So I want to talk about disruptors. Now, if I want to disrupt the market, I got to look at some technical challenges that I might have. One technical challenge is for a given set of resources, your processor, I might not have enough clock cycles to achieve it. So what does a disruptor do? They improve the efficiency of the customization of the core so that I can do my activity in the desired amount of time. Another one is my core might be too much energy. So what does a disruptor do? They actually modify, design the core so the minimal amount of resources that are required to achieve the application are used, and therefore I optimize my power. Or another thing is my solution is too large, too expensive. A disruptor knows how to redesign the core, optimize it, and customize it for optimal performance. For example, using a small core to perform a larger core's function. Resources might not be available in a standard core, and I want to create a new category. For example, say some type of new security processor. So those are examples of what a disruptor has to do. Now, if we take a look at it, we did a demo at the EU RISC-V Summit this year where we showed some of these basic concepts, where we took a core that's about the size of an M0 Plus, and we added the DSP functionality and neural network on this little core, and we wanted to run it at 40, or put it in a 40 nanometer technology, because that was the technology where the sensor would actually go. Now, if I take a look at that, I have a problem where I can't go fast. I have a relatively large process node, and I only have 25 megahertz available. To make that possible, I had to use customization to improve the efficiency over 4x. But the important thing about it was I actually reduced the power by over 6x. So this is an example of a disruptor or disruption. Now, to get a little bit more detailed to what we did was here is the general matrix multiplication loop or routine for neural network. And we were able to accelerate that by 8x using custom instructions. Now, we've actually, if we re-architect actually no new instructions, but just rewrite the inner loop, we now know how to get it to 16x compared to a standard RISC-V C implementation. Now, if we take a look at that, we have a core that's about the size of an M0. We added a few additional resources, so it's a little larger than an M0, that is now going to achieve twice the performance for the general matrix multiplication than an M7, which is a much larger core, much larger resources, and more power. Now, that's just a little bit example of what disruptors or disruption is. Now, let's take a look at what this topic is all about. Is an optimal solution solves need. I have those disruptions of how I'm going to solve that, but I need to increase profit while minimizing risk. Risk is fear, uncertainty, and doubt. Now, let's take a look at what some of my fears might be. I might have a fear is, how do I verify? I'm a small company, or I don't have a resource team available to verify customization. That's a fear. How am I going to verify and make sure that my core is something that I can go to market with? Uncertainty. Will my software application or my third-party software able to access all the customization that I've added to actually realize the performance of what I'm trying to disrupt the market with? Or doubt. What are the engineering problems that I have to solve? Did I solve them? Are there real examples that I've actually can say that this methodology reduces the fear, uncertainty, and proof? I've actually show you that I can remove the doubt. Now, let's take a look at fear. How am I going to resolve fear? Now, at Codasip, we actually have a new family of cores coming out. We have an L110, which is roughly the size of the M0 Plus, and the L730, which we just announced last week, which is like an M7. And these things support what we call bounded customization. Now, these cores are completely formally verified. They are achieving best-in-class area and performance. Now, in combination with our software tool, Codasip Studio Fusion, we actually support what we call bounded customization. Now, what bounded customization enables is now you can add new instructions to the core, but not break the verification of the core. So if I don't break the verification of the core, I can remove this fare. All you need to do is ensure that the new instruction performs what you want it to do. So we're removing the idea of fare by providing you a fully verified core and a mechanism to add custom instructions that do not break the verification of the core. What I like to say, you have an SoC team, now you have a custom processor team. You don't need a full processor verification team to optimize a core. And we'll show that to you in a few minutes. So bounded customization enables you to add custom instructions without risk. Now, how do we do that? Well, once again, we build this technology upon verified IP cores. And we don't allow you to change any. You can actually view all the files of the core, but they're only readable. You can't write to them. We ensure that you cannot break the core by allowing you to actually access those files or write to those files. We first allow you to do what we call configuration. You want to get to the closest space to your customization or your custom core that you want. Then after that, you can add your custom instructions. Now, if you take a look at it, what we do through bounded customization, you can almost imagine that we're adding a custom execution unit. And we're adding those custom execution units between pipeline registers. So if you think of it, if I'm between pipeline registers, anything to the left of the first pipeline register or everything to the right of the pipeline register is not being affected. It's using all those resources both to the left and to the right. And by doing this, we can guarantee your verification. Now, a little bit more detail on that is we have this entire methodology built out where you have this verified core and you have this verification environment that you have access to afterwards. And it includes models and random instruction generators to validate that your instructions are doing what you want to do as well as not breaking the core. So we provide all the tools to help you in the verification effort as well as guarantee that you cannot break the core. So we are removing the fear of customization. Now, the next part of the fear, uncertainty, and doubt is removing uncertainty. Now, you take a look at uncertainty. Now, if you look at the ARM model, they use libraries CMSIS. And what does CMSIS really do? It abstracts the hardware, the core, from the software application. So if you write a CMSIS, if you use CMSIS, for example, FFT, I can run that software application on M0+, M4, and M7. And when I compile it, I will get the optimal solution for each of those cores because the CMSIS library abstracts the hardware from the software application. If I compile for an M4 or M7, it's going to set a flag called ARM DSP math, and therefore we'll use the ARM DSP instructions of the ARM4. Same basic idea. Codasip libraries will enable direct ports of ARM applications onto our cores. So what you're talking about here is if you have an application that is running on an ARM and it's using libraries, it will run on the RISC-V. And if I come up here, we do provide all the access to the custom instructions as well, so that if you have code that you actually write yourself and you want to directly access those instructions, you can, but we also abstract it through the libraries. We take a look at it. Here's a good model of it. I have a software application, and depending upon how I recompile it to the targeted processor technology, it will take the appropriate libraries from either the ARM or Codasip and give you the software stack. So these software stacks are identical. So as an example here, we are doing an FFT. We're using the same ARM. It's a little strange writing RISC-V code and you're actually calling it ARM. But I mean, if you really think of it, who has the largest base of software? It's not RISC-V, it's ARM, right? So we have to abide by that. So we call this ARM function, and if it's compiled to RISC-V, it will, this bottom one here is not using any of our DSP extensions. So it is just compiling it, just C code. And so as a benchmark, I'm just saying FFTs per 100 megahertz. And so we consider the L110 to be an M0-like core, but like I mentioned before, first best in class in performance and area. We're outperforming an M0 plus. Now I add 4 instructions. They're nothing too complex. And you can see here, I have a core that's a little larger than an M0 plus that is actually performing more DSPs per second than an M7. And through the abstraction of the library, any application that is using the this ARM7 FFT now will use our L110 plus DSP extension. I have removed uncertainty, and now I've proven I've removed doubt. So that's what we're trying to do, remove fear, uncertainty, and doubt. Now, I like this quote. The art of processor customization is the balancing of innovation with risk, right? I have another quote. I have a talk tomorrow as well, which is software engineers are the new processor engineers, and I have a similar quote in that. But I really like this quote because our job is to create products on schedule, on time, that meet the required application. Now, what we've just talked about here, by removing uncertainty and doubt, we've removed the negative weight of going with RISC-V, but we're also showing the performance that we've gained through the customization, that we have now moved the weight to the benefit of going customization by removing fear, uncertainty, and doubt. So that's my presentation today. I would like to, does anyone have any questions?
Yeah, sure. Hang on. Let me give you the microphone. We are recording.
Gosh, it's really official now.
Yeah, so I know that Tensilica had very similar capabilities for a long time. But the more difficult part is adding those custom instructions into your compiler. So for example, if you're adding new data type like a complex type, and then you want to take existing software, just recompile it with a new instruction and get the performance benefit, that's usually the challenge, right? For the compiler to automatically understand what the new instruction does. Now you can always obviously write an assembly, but that's taking a step back in terms of software development productivity. So how do you address that issue?
So that's a good question. So depending upon the complexity of the new operation instruction, as you develop it in the Codasip Studio environment, the compiler will automatically realize, and it will become compiler aware for the more simpler instructions. But as you mentioned, the more complex ones are really become too difficult for the compiler. So as you generate the custom instruction, it automatically creates the intrinsic. And this is where you use the hardware abstraction of the library. So someone does have to port the library that says, just like ARM does, right? ARM has an M4, M7 part of CMSIS with their custom instructions. We will have a version that has our intrinsics with our new custom instructions. So it all depends on how complex. Some of the instructions will become compiler aware, and some other ones will have to be abstracted to the library or directly accessed via intrinsics.
Yeah, it seems if you could express your new instruction in terms of compiler primitives or some kind of IR representation so the compiler can then automatically take advantage of it, might be a good step. So just a thought.
Yeah. I'm not the compiler guy. I would have to say I'm a hardware guy. But we do, like I say, like we did a hackathon last year at EU RISC-V Summit where the students created the accelerated Percepton with custom instructions. And when they created it, those instructions actually became compiler aware, and they did not have to use intrinsics. Another question? I like this. You know, when I was taught at CU, you know, I don't always get questions from my students, so this is fun.
Thank you so much. So I understand the value of having independent verification paths for the core and the custom extensions. At least the diagram that you showed, the customization between pipeline stages is kind of simplified. What if the custom instruction is stateful? Doesn't that add a much larger layer of complexity there?
Yeah, so there is, so you could have stateful information, and actually some of our custom instructions have stateful. So the real key is whether it's idempotent, if I pronounce that correctly. So if it's not idempotent, normally we don't have any problems with stateful information, but if it's not idempotent, then you have to be careful with interrupts.
Okay.
All right.
What is idempotent?
Idempotent means that if I start the instruction,
Okay.
and I should always end with the same result. So imagine that I have a fur filter and I have a history table, right? If I begin the fur filter, I update the history table before I finish, and I have an interrupt, right? When I come back from the interrupt, they'll start the fur filter instruction again, but now my history table has changed, right? And therefore, I will get a different answer. So it's not idempotent. But the way around it is, if you know how to design it properly, is you don't update the history table until you commit the instruction. And now you have an idempotent instruction that has state, but you won't have any issues with it, like with an interrupt.
All right.
So you just have to be aware of it.
Thank you.
Good question.
So we have 50 seconds. Any other last question?
Well, thank you very much. If you do have any questions or you'd like to learn more about it, we do have a booth in the expo area. Thank you very much. Have a great day.